EPSP Connects seminar of the season. Some of you might know this, but for those of you who might be new, the purpose of this series is to bring the community together to help establish connections between people who might not be able to interact with others in a different setting. So we're very happy to have you here. I would like to thank all the EPSP Connects team members who helped plan and organize. This is the first time that my office phone makes noise. That's quite the coincidence. Sorry about that. I would like to thank the whole EPSP Connects team who organized this series, who reach out to potential speakers, coordinate with them, who advertise in social media and make sure that the series information is up to date on the website. And a huge shout out to Jimmy Geilinger, who makes sure that we have the Zoom meeting room ready, that the registration links are working, and that the talks are streamed and later uploaded to the YouTube channel. So joining me today as co-host is Vishwadeep Halikari, who will help us with the Q&A session at the end. How are we going to deal with questions, Vishwadeep?
Yeah, so please post your questions in the chat.
Did I do something?
And Roberto and I will monitor them. For those listening to our live stream on YouTube, we will also keep an eye on those further questions. And if you prefer, we are also able to ask you to unmute and ask questions directly.
All right, sounds good. Our speaker today is a Boricua and Latino scientist. I don't know, did someone say Wepa?
That's strange.
But I think I heard it. Anyways, I am very happy to be hosting Dr. Francis Rivera Hernandez, who runs the Planetas
Anybody have any ideas?
At Georgia Tech. May I ask, yeah, thank you, everyone to mute themselves, thank you.
Okay, but why aren't we hearing them?
Oh. Yes, I am unmuted, right? Can people hear me? Because it's been going on and off. Yeah, all right. Dr. Rivera Hernandez holds undergraduate degrees in geology and astronomy from the University of Wyoming, an MS in Earth and Space Sciences from the University of Washington, and a PhD in geology from UC Davis. In 2018, she joined the Faculty of Earth and Atmospheric Sciences at Georgia Tech, where she is an assistant professor and the co-director of the astrobiology program. Her research focuses on understanding planetary surface processes and environments, both modern and ancient, as recorded in sedimentary deposits and terrains. For this, she uses a suite of techniques involving remote sensing, analog field and lab studies, and numerical analysis. Before moving on to the talk, I do want us to reflect on the great privilege we have to be sitting here and enjoying the seminar. There are people out there in different places, particularly in France's home country, struggling with the aftermath of Hurricane Fiona. So perhaps you might consider supporting them. There are simple ways of doing it online. And without further ado, the title of today's talk is From Grains to Landscapes, Reconstructing Martian Environments on Multiple Scales. So please take it away.
Great. Thank you so much, Roberto, for that great introduction. And thank you for inviting me to talk to you all today. As Dr. Fernandez just said, I'm Dr. Frances Rivera Hernandez, and I'm an assistant professor at the Georgia Institute of Technology, or Georgia Tech, as it's most commonly known, which is a university in Atlanta, Georgia. And Dr. Fernandez has already mentioned this, but this is a little bit about me, but most of my research focuses on studying sedimentary rocks and terrains to characterize ancient and modern environments on planetary bodies, mainly Earth and Mars. And I do this to obtain information about their past climate and water availability, and to determine if these water environments in particular had conditions habitable for past life. I also conduct field analog studies on Earth to help characterize past environments on Mars, mainly in polar regions. For example, here on the left is a picture of me back in 2015 studying deltas and lake bottom sediments in a frozen lake in Antarctica. And then on the right is a picture of the Curiosity rover, which is a mission that I'm currently involved with, and I do a lot of work with rover images, and I'll be talking a little bit about that work later on today. In addition to research, I'm also heavily involved with multiple organizations helping to increase the representation of Latinx in the geosciences, but also providing a support and mentoring network for all of us. And so these include the Society of Latinx Hispanic Earth and Space Scientists, the Geolatinas, which is an international group of Latina geoscientists, and the Boricua Planeteers, which is a group of Puerto Rican space and planetary scientists. And as Roberto mentioned, I myself am a Latina from Puerto Rico, which is currently recovering from a hurricane. And so I also encourage all of you to donate to a variety of organizations that are sort of helping to rebuild and provide resources to Puerto Ricans. As far as these organizations that I have here on the slide, they all have an online presence. We're on Twitter, Facebook, and Instagram. Geolatinas in particular is quite active on Twitter, and so maybe you've heard of Geolatinas before. But if you're interested in learning more or joining, you can feel free to email me or to look us up online. We're always recruiting new members and also allies. And so again, if you're interested in learning more, feel free to reach out to me. Great. So enough about me and sort of advertising. As the title of the talk suggests, I'm going to be talking about reconstructing ancient environments on Mars using data at the grain size to landscape scale. And for most of my talk, I'll be focusing on some of my postdoctoral research, mapping deltas on Mars to revisit this global ocean hypothesis for Mars. And then for the last 10 to 15 minutes or so of the talk, I'll present some of my active research focused on conglomerates with the Curiosity rover. And so the last part of my talk is very preliminary, results and data that, like I said, we're actively sort of working on in my group here at Georgia Tech. But for both parts of my talk, my research is focused on Gale crater, or the Gale crater region of Mars. Gale is the home of the Curiosity rover. It's located in the equatorial regions of Mars, as shown here on the left. And so this is a global image of Mars, highlighting the location of previous missions. And Curiosity is right here with the star. And as I mentioned, that's it's in a Gale crater, which is shown here on the right in this black and white orbital or satellite image of the crater. And the Curiosity landing site is shown here with the star. And then one of the interesting things about Gale crater is that it has this massive mound in the middle called Mount Sharp that consists of stratified sedimentary layers. And currently the main goal of the Curiosity mission is to drive up this mound. And that's sort of what we're actively doing. Sorry, I'm meeting a couple of folks just to make sure that, there we go. Great. And Gale crater, it straddles what we call the dichotomy boundary of Mars. It's probably one of the most striking features of the red planet. And it's this boundary which separates the smooth northern plains to the more rough southern highlands of Mars. And Gale crater is sort of smack in the middle of all of that. And there's evidence that regionally water flowed potentially, in rivers from the southern highlands down into the lowlands, where it pooled locally within Gale crater and surrounding regions in lakes and possibly this northern global ocean. Based on crater counting, Gale crater formed about the time when the climate on Mars was changing from one that was wet and potentially warm to the mostly cold and dry conditions of today. And this is shown here. There's a very simple geologic sort of time scale for Mars. And this global climate happened here, which is 3.6 billion years ago. And during this time, the composition of alteration minerals on Mars was also changing from mainly clays to sulfates after that transition. And this is something that's actually observed in the lower reaches of that central mound in Gale crater. And so it's possible that environments preserved in Mount Sharp record this climatic change on Mars from wet to dry conditions, which is one of the main reasons that we sent the Curiosity rover to Gale crater. While we do know that the climate must have been different in the past, we don't really have a community consensus for what that climate was like. We do have two leading scenarios. The first is what we call the cold and icy Mars scenario that's shown here on the bottom left, where Mars was cold with water primarily in ice form. However, periodically ice melted to form liquid water to produce rivers and lakes. And very much what is the case for Antarctica, for example. There are rivers and lakes in Antarctica that also persist at temperatures below zero, or mean annual temperatures below zero, which is why I'm really interested in Antarctica. The other scenario is this sort of warm and wet scenario where, shown here in the bottom right, where Mars would have been warm with abundant liquid water to sustain rivers, lakes, and also possibly this northern global ocean. And so it would have been more Earth-like. And this lack of consensus is one of the main reasons that we are still very much interested in characterizing past environments on Mars and determining water budgets in particular. And so what environments were present on early Mars, and how much water could they have stored or transported on the surface of Mars? And so within this very broad scope, I'll be addressing two main questions for my talk today. The first, from geomorphology, how much water was sustained in the broader Gale crater region in multiple lakes or a global ocean? And then for part two, how does grain size and also rounding vary in conglomerates in Gale crater, and how much and what does that imply about Mars's paleo-hydrology? And so I'll start, of course, by addressing the first question. And so we'll be starting at the landscape scale for the first part of my talk. And this is research that I started as a postdoc at Dartmouth College, working with Dr. Marissa Palousis, focused on mapping deltaic deposits in the Gale crater region. And we actually are still working on this project, but the data that I'll be showing today is mainly from my postdoctoral work. All right, so this is an example of a deltaic deposit in the Gale crater region. This is an actual image of a deltaic deposit. And we can see that the landform here, this delta, emerges from an incised valley that's marked here. And it has this beautiful arcuate shape with a stipply dipping front that's very characteristic of deltas. And in particular, this one is between the shape and that stipply dipping front is very characteristic of Gilbert type deltas. And on Earth, we know that deltas form in standing bodies of water. And so they form essentially in lakes and oceans. And so here on the left is just an example of a pair of deltas that are actively forming in a lake in the Tibetan Plateau. And then on the right is an example of a delta that's forming in Greenland here in the ocean. And in this example here on the right, we can even see that a very similar arcuate shape to the delta, and also that incised sort of valley. Again, very reminiscent of that image from Mars that I showed in the previous slide. And what's cool is that the paleo-hydrology, so the past water information for the bodies of water that these deltas formed in, can actually be reconstructed by using the elevation of the front of the deltas. And so these are essentially proxies for paleo water level. And so this is where the stable water level was when the delta formed. And so in this example, that delta front would be in this dashed blue line here. And so using these very basic concepts, there was a previous global delta study of Mars by a previous group that interpreted that deltas that fall along the dichotomy boundary of Mars formed in a northern ocean, where again, the dichotomy is this feature here that separates the northern lowlands from the more rough southern highlands. And we can actually see that in this topographic map of Mars, where we can see that the lowlands is considerably lower than the highlands. And then the deltas from that study are marked by diamonds, and they fall near that boundary. And the front elevations of the deltas were used to reconstruct the paleo shoreline here in magenta. And so again, this proposed ocean would have formed in the northern lowlands of Mars. Interestingly, the highest concentration of these deltas occur in the Gale crater region, and that's highlighted here with this orange box. And one of the interesting things about Gale crater is that it doesn't have any geomorphic evidence suggesting that it was ever part of a northern ocean. Instead, data suggests that deltas or deltaic deposits in Gale crater likely formed in lakes. And this is actually research that my former postdoctoral advisor, Dr. Marissa Pelusis, did for her PhD. And this is a figure that she made here on the left. And again, we have this black and white image, orbital image of Gale crater. And the closed contours are the reconstructed water level stands for these past lakes. And then the blue are the deltas that are interpreted to have formed in these lakes. And then the yellows are alluvial fans. And on the right is an example of one of these beautiful deltas called the Pancake Delta. And so essentially these observations challenge the idea that other dichotomy deltas formed in a global ocean and that they instead formed in lakes. And this actually may have huge implications as the Gale crater region, as I mentioned, has the highest concentration of these deltas, and deltas have been one of the strongest evidence that we have for a northern global ocean. And so from this, of course, I think a natural question to ask would be, do deltas in the Gale crater region record a global ocean? So do other deltas in this region record a global ocean? And here we're just focusing on the Gale crater region because it does have the highest concentration of these deltas. And we are expanding to other research. We actually just got a grant funded about a year ago to sort of expand our analyses. But today I'm going to be just focusing on the Gale crater region. And so the reason that we care about this is that if we do have evidence for a past ocean, that tells us that at least for some period of time, Mars had higher surface pressures and a climate warm enough to sustain liquid water on its surface. And that it also had enough water to fill that lowland basin in the northern part of Mars. And so we can essentially get estimates for water budgets. And so this would essentially help support the warm and wet Mars scenario. And there have been several pieces of evidence that have been used to suggest the presence of oceans on Mars. And again, today we just focus on deltas as they're one of the strongest sort of geomorphic evidence, pieces of evidence that we have for this northern ocean, or that have been proposed as evidence for this northern ocean. All right, so to address this question, I analyzed new and previously identified deltas with updated imagery and derived topography. And for my inventory, landforms, or fan-shaped landforms, were classified as deltas or alluvial fans. And so from orbit, it's quite difficult to distinguish alluvial fans from deltas. You really do need topography to do that. And deltas were identified by their arcuate form, low gradient tops, and stipply dipping fronts, as shown here on the bottom left. And so this is another example of a delta in the Gale crater region, and we have a profile or long profile across that from A to A prime. which again shows that again, the characteristics that I just described with that low gradient top and the steeply dipping front, where again, the delta front elevation can be used as a proxy for paleo water level. And in contrast, fans have concave to linear long profiles, such as this example here on the left, which is an alluvial fan in the Gale crater region. And again, very similarly, we have a long profile from B to B prime, showing the shape of that alluvial fan, which is quite different from the case on the left. And of course, unlike deltas that form in sustained liquid bodies of water, alluvial fans form subaerially, and so they do not form underwater. So they represent different depositional environments. And so zooming into the Gale crater region, again, here in this, and so Gale crater, I always have it marked. It's always in the middle. It's one of my favorite craters. The orange diamonds here are the locations of the deltas from that the previous study by those other researchers. And again, the background image is just the regional topography now in black and white. And I'm going to add the my updated delta inventory with white diamonds from our study here next. And so that's what I have shown here. And so I can go back and forth just to show you again. And hopefully one of the things that immediately pops out is the high number of deltas in this region. It's just littered with them. But something else is that they also occur in clusters. And you can see some of those clusters here, if you can see my cursor, and also, of course, in Gale crater, and then further down here as well. And we can actually see this trend a little bit better in plot form. And so here in this plot, I now have delta front elevation, so the elevation of where the dip in that landform changes. And then on the x-axis is longitude, which is used here to represent location from left to right or west to east on Mars. And one of the things that I might be able to see is that regionally, deltas are commonly clustered in groups, and those deltas that are near each other have similar delta front elevations, and thus paleo water levels, or that represent this, similar paleo water levels. And the different delta groups are highlighted by circles, and then the blue line here is the paleo water level for that hypothesized global ocean from that previous study. And hopefully one of the things that pops out is that there are very few deltas that have delta front elevations that are even close to that proposed ocean water level. And the Gale crater deltas are all the way down here. They actually have they deviate the most from that proposed global ocean water level. Instead, what we do see is that the geographic concentration of deltas with similar delta front elevations suggests that deltas within these groups formed in the same standing body of water. And so by averaging the delta front elevations within each of the groups, we were able to sort of use that as an approximation for, water level proxy for the basins in which they formed in. And by doing that, we actually found evidence for 10 paleo lakes, 4 of which host multiple deltas. And the largest, which is the one in the top left, would have been a little bit smaller than Lake Ontario, just to give you a sort of a sense of scale. And then together, these 4 lakes would have stored about 5 centimeters global water equivalent, which is this GWE, which is the water depth if it were spread out equally on Mars. And so it's actually not a lot, 5 centimeters GWE. Previous estimates for that inferred ocean is 550 meters global water equivalent. And so the water budgets are drastically different. And again, that's really important because that can give us a sense for what the climate was like on early Mars and what the climate actually had to be able to sustain these different water budgets. The presence of these lakes has also been supported by initial geomorphic analyses. And this is work that Oak Canine did when she was an undergraduate at Dartmouth College. They are now a grad student at Caltech. And what they observed is that basins tend to have smoother textures compared to surrounding topography. And some of these actually have possible shorelines along their perimeters, as shown here on the right. And so by using these characteristics, and so smooth versus rough, and actually mapping out some of these potential paleo shorelines, Oak was able to independently map the location for one of these basins. And again, this is helping to support our interpretation that these are indeed paleo lake basins. And this is something that we're hoping to do for more of the basins that we've identified in the study. As I mentioned, we just got funding from NASA to sort of extend these analyses, and this is work that's being led by Dr. Marissa Palousis at Dartmouth College, and one of her current grad students. All right, so going back to the original question, do delta deposits in the Gale crater region record in Northern Ocean? Short answer is no. The deltaic deposits likely formed in paleo lakes, and actually a series of paleo lakes. However, we really can't rule out the global, Northern Ocean hypothesis for Mars. There are other features that may have formed in an ocean, and these include other surface flow features called valley networks that terminate along the dichotomy boundary. And so these are shown here on the left. And so again, this is a topographic, a zoomed in topographic map of Mars. And the red here are these features that we call valley networks. They look like channels, and they do terminate along the dichotomy. There are also previous studies that have mapped features that they interpret to be paleo shorelines, although recently higher resolution data have shown that these do not represent equal potential surfaces, which means that the elevation of these proposed features are not the same throughout. And actually, in some cases, they deviate by something like 1,000 kilometers plus along those mapped features. And so and beyond that, we actually don't really know where these features are located due to inconsistent mapping between publications of the same mapped levels. And so what's happened is that in the original, people essentially traced original maps, and with each tracing, it's kind of playing that game called telephone. With each tracing, the locations have shifted. And so we don't even, depending on the paper that you read, the location of those shorelines might be completely different, even though they're called the same thing. And this is work actually being done by a colleague of mine, Dr. Scholes, who's now a researcher at JPL, and who has spent a lot of his time sort of trying to recreate and find some of these features. So if you're interested in that, please check out several of his papers. That he has had several papers on this in the last several years. Also, it is possible that there was an ocean and that ocean dried up into small lakes. And so, again, we could have had a larger water body, and then it shrunk over time. And so we have this evidence for lakes because that water budget changed over time. However, if this was the case, the deltas should have a geomorphic record of that. And so essentially the front of the deltas should be tracking the water level of the ocean. And so if the water level was, if the deltas were forming in an ocean at a particular water level, and that water level was dropping over time, then the front of the deltas should also have changed over time. And so we would see sort of stepping features on the deltas, which we don't see. We don't see that progradation or active progradation forward towards a changing water level. That said, we do have evidence that some of the deltas are overlain by alluvial fans. And so we have deltas, and then right on top, we have evidence for alluvial fans, which may suggest a change from wet to dry conditions or reactivation of a catchment later on in a different point in time, which is pretty cool. And then just to kind of wrap up this part of my talk, I did want to end saying that we have a new rover on Mars called Perseverance, and it's actually exploring a new crater called Jezero Crater. And it actually has another one of the deltas previously interpreted to have formed in an ocean. And I have it marked here in that original map that I showed. And very similarly to Gale crater, there's no geomorphic evidence for that delta to have formed in an ocean. Instead, there's a lot of geomorphic evidence for that delta to have formed in a paleo lake. And unlike in Gale crater, we're actually going to be able to explore, or we have actually been exploring this delta in, sort of boots on the ground with the rover. And so hopefully with Perseverance, we'll be able to learn a lot about the conditions and environment in which this delta formed up close, which is pretty cool. And so here on the left is just a black and white image of that delta that I was talking about that's in Jezero crater. And then the star is the landing site for Perseverance. And throughout its mission so far, it actually has been able to characterize not only the main delta sort of feature, but also this other little mound down here called Kodiak, which actually we found out is a deltaic remnant. And we can even see beautiful cross beds here in this sort of butte. And again, this Kodiak mound in Jezero crater. And like I said, hopefully we're going to be learning a lot more, and especially the closer we get to the main delta, we'll be able to get a lot of great pictures. All right, so to sort of just wrap up this part of my talk, dichotomy deltas formed in different standing bodies of water. And in the Gale crater region, most deltas likely formed in lakes, not an ocean. And they would have recorded together about 5 centimeters global water equivalent, which again is that water depth if you would have spread it out over the surface of Mars. And then detailed geomorphic mapping in this and other regions show actually similar interpretations. I didn't mention this, but there have been more recent studies that of other dichotomy deltas in other regions of Mars that have just come out this year that also show that those deltas also likely formed in lakes and not a northern ocean. And so this is really where I think future work should really focus, and this very detailed geomorphic analyses to sort of help get more information about the environment of these deltaic deposits. All right, so now we're going to switch gears a lot. And so for the second part of my talk, again, we're going to be looking at the grain size in conglomerates in Gale crater. And so we're now going from the landscape scale to the grain scale, and in particular with how we can use conglomerates in Gale crater that have been imaged by the Curiosity rover to provide insights to the hydrology of early Mars. So in addition to the landforms that are in Gale crater and in this region that provide evidence for surface runoff, we also have sedimentary rocks that are much older than some of the features that I was just talking about. And I think that conglomerates are super, super cool because they are sedimentary rocks that consist of other rock pieces. And one of the key environments that they can record are rivers. And with Curiosity, we actually got really, really lucky. It just so happened that the rover landed on conglomerates at a site that we now call Bradbury Landing at the toe of the Peace Vallis fan. And so earlier on, I was showing that black and white image of Gale crater, and I said, there's the location of deltas and some fans. We actually purposely landed Curiosity on the toe of one of those fans called Peace Vallis. And like I said, it just so happens we just landed on these beautiful conglomerates. The rocks were actually exposed while the rover was descending, and dust was blown away from the jets that was helping on the sky crane that was helping sort of descend the rover to the crater floor. And the jets essentially helped blow away dust from the Martian surface, as shown here on the left. And so we got to see these very beautifully exposed conglomerates on the right, exactly right where we landed. And it's some of the first images that we took with the rover were of these conglomerates. And after landing, we were able to image 3 of these rocks up close. And from these images, Dr. Becky Williams and others noticed that some of the clasts were very well rounded, like the one on the image here on the left. They also noticed layering, grain to grain contact, and subtle imbrication of the grains, which is essentially when a grain is piggybacking on another grain. That's what we call imbrication. And with other available geologic context, the grains in these rocks were interpreted to have been transported by rivers on an alluvial fan, as shown in the cartoon here on the right. And so we can imagine that there were rivers emanating or originating from the crater rim, transporting grains that were, or they were transporting grains by rivers that were deposited and cemented to then form the rocks that we see today. And so using images again of three rocks, Dr. Becky Williams and others performed grain size analyses, and together with paleo-hydrology equations determined that the paleoflow velocity for those ancient rivers would have been 0.2 to 0.75 meters per second, which is not that high, but it's sufficient. And these data were actually a big deal at the time, because not only did it provide the first ground-based evidence for rivers on Mars, they also provided the first ground-based paleoflow calculations as well. Since a lot of the work that we do for past rivers on Mars is from orbit, this is really the first in situ or the first ground sort of analyses that we had for these. So they're a really big deal at the time, and they still are. Great. And so after Bradbury Landing, which again is that landing site, the rover actually encountered other conglomerates along its traverse. This is something that a lot of people don't know, since we only had that one major paper, but we actually did see conglomerates in other parts of the traverse. And so the traverse is just the regions in which the rover has sort of trekked. And some of these locations are highlighted in the map on the left with the yellow points, and in the stratigraphic column here on the right with stars, where a stratigraphic column, again, is just a graphical representation of grain size with elevation in this case. And so this is just showing on the right the diversity of rocks that were encountered by the rover at different elevations. And these, of course, include conglomerates, which we can see. So we saw a diversity of mudstones and sandstones that were then interbedded with these conglomerate lenses. And so even though we did see a lot of these conglomerates, a lot of these, however, haven't been studied in enough detail, especially those that are not next to other outcrops of interest. And so as many things that happen with missions on Mars, we have very short attention spans on these teams. The rover is constantly moving, and sometimes we spend more time on certain outcrops than others. And so same thing has happened with these conglomerates. And so because of that, their depositional setting and hydrologic history has not really been well constrained, at least not the full sort of story. And so this actually has been a particular focus of the research that my lab group has been doing here at Georgia Tech. And as I mentioned earlier, this is active research. And so a lot of the data that I'm going to be showing moving forward is really just preliminary. So it's fresh from that fresh work that we've been doing. And this also includes work that's not only being done by myself and REU students that I've had, but also one of my graduate students, Tatiana Gibson. And so I'll be showing some of her data as well later on. But today, however, I'm interested in talking about the paleoflow history that these rocks may record. In particular, some of these conglomerates occur near lake deposits at two locations, which suggest changes over time. And so that suggests to us that potentially we had a fan alternating to a fan delta setting, which again may be related to changes in water availability. And again, that's because in at least two locations we have conglomerates, adjacent to lake deposits. And so with this in mind, one of the things that we're asking with this research is whether the conglomerates record changes in flow energy and water availability over time on early Mars. And one way to determine this is to measure the grain size of grains and rocks, as these reflect the energy of the environments that they were deposited in. And on Earth, this is actually something that we can do quite easily. We would just go out in the field with a hand lens or a grain size card like this one shown here on the left, so that we can measure the size of grains. However, we really can't do that on Mars. And so for Martian rocks, we use images. And actually, Curiosity has 17 cameras, and we use images from those cameras to essentially characterize the outcrops and rocks that we encounter. But in particular, there are 3 cameras that we can use to measure the size of grains and rocks. Depending on the grain size or rock type, we will use different cameras. And so MAHLI, or the Mars Hand Lens Imager, it's a camera that's on the rover arm. And that's the one that produces the best high resolution images that we can really see to get at really fine grain sizes. And so we can actually see coarse, silt, or larger. And so, 60 microns, something along those lines, or I mean, if it's really good, maybe 50 microns. With the other 2 cameras, there's the mass cams, which are located on the rover head or mast. And so the mass cams are located here at the bottom. And there's also the CamCam remote micro imager that's located on the rover eye. And these are better, or they're more sensitive to coarser grains. And so with CamCam, we can still see, very fine sand and larger. And then for the mass cams, that's better for medium sand or coarse sand and larger. For conglomerates, conveniently, since the class are so large, we can use images from all cameras. However, the MAHLI camera, which is the one that produces the high resolution images, it takes a lot more energy to use because it's located on the rover arm. And one of the things that we have to be careful with the rover is energy consumption, because we use nuclear energy, we have batteries. And so every time we make an observation, we're using up energy. And so because of that, we actively don't use the MAHLI camera quite frequently. However, the CamCam RMI camera, we use all the time. It takes very low energy to use. We can still get, again, information for very fine sand and larger. And so because of that, with this research, I've purposely have started with the CamCam remote micro imager images because we have just more of them. And so that was just a really good place to start, although we are looking at images from all of the cameras in our research. And so for today, I'm mostly going to be focusing on those images, the ones from CamCam. All right, and also, I'm also only going to be showing data from one main region that we call pre-Darwin, which spans from the sort of the landing site, or really Yellowknife Bay, which is a region I didn't talk about, to something that we call the Darwin outcrop. We love names and planetary, and all the outcrops and rocks have names. And so very similarly, this whole region, like I said, that I'm going to be talking about is called pre-Darwin. And it's highlighted in this sort of red bracket. And I'm also going to be comparing that to data from another region higher up in stratigraphy called Amargosa Valley, which is highlighted in the blue star all the way in the bottom here. And so these deposits represent younger conglomerates compared to those in the landing site and then the pre-Darwin. All right, so the data that I'm going to be showing is, of course, mainly grain size data. And grain size is key because it can provide information about paleoflow energies. And essentially, as higher energy flows are generally required to move larger grains. And as I already mentioned, I'm going to be using images from that remote micro imager. And there's an example image here on the left where we can clearly see grains or clasts in this conglomerate. And I already mentioned this, and I know in the interest of time, I will say that for this, we purposely used a grid by point technique where a grid was superimposed on the RMI images, and then grains were essentially measured or traced at the grid intersections. And we typically measured 100 grains per image to really get a good number. And then with that, we calculated D50, which is the median grain size, and then also D84. And then with that, we were able to get paleoflow energy information. And a lot of the grain size data that I'll be showing was actually acquired by an REU student, not this summer, but the previous summer, so summer 2021. Maggie Burdell from the University of Georgia. Great, and so here are some results for that pre-Darwin region. And so this plot is elevation versus D50, which again is just the median grain size. And what we see is that the median grain size for these rocks is generally similar. And so the D50 values are around 3 millimeters. And it may not seem like a lot of number of rocks, but like I said, that original paper only did 3. And so now we have 12. And so we've been working on this slowly, but we're adding to this data set. And like I said, one of the main observations is that at least for this region, the D50 is quite similar. And we interpret this to suggest that the energy of the water flows that transported those grains was generally the same for that stratigraphic interval. And we've also have performed preliminary paleo-hydraulic calculations, which shows that these past flows would have had depth average velocities spanning 0.13 to 0.45 meters per second, which is still quite low. And comparing this data to rocks that are older in Bradbury Landing, so those are the original 3 rocks from that original study, and then from Amargosa Valley, and this is work done by a collaborator, Dr. Katie Stack and Christina Seeger. We see that the pre-Darwin rocks have D50s that are lower than Bradbury Landing, but they're higher than those at Amargosa Valley, which are shown again here on the left. And these results suggest that the water flow energies varied and potentially decreased over time, which may suggest that possibly lower water availability due to drying or cooling conditions. And so if we actually can compare these paleoflow velocities with each other, because we do have similar calculations, we see that while there is some overlap in values between pre-Darwin and Bradbury Landing, these are still 20 times higher than those at Amargosa Valley, which have really low depth average velocities. And then we can also compare results from Gale crater to Jezero crater. And so the conglomerates and so Jezero crater is where the Perseverance rover is exploring. And the conglomerates in Jezero crater have D50 values that are 5 times larger than those in pre-Darwin and 32 times larger than Amargosa Valley. And so those flows in Jezero were quite energetic compared to those that flowed in Gale crater. And this suggests that the depth average velocity of the Jezero flows were 5 times higher, which may suggest warmer or wetter conditions. And then I know that I'm kind of going low in time, and I'm almost done, I promise. We are really excited about all of this work. Like I said, this is all active research, and future research is going to be focused on expanding our analyses to other locations and doing detailed sedimentological work. And again, this is actually work that I also got funded to do through NASA. I got a PI grant funded to sort of do this work. And I actually have a grad student, Tatiana Gibson, who has been working on characterizing the rounding for some of these conglomerates. And I just wanted to share some of that data with the last couple of minutes. And so this is Tatiana here on the top right. And she's been exploring different techniques to approximate rounding of clasts from images, which is quite difficult to do. And at the moment, she has started with something that's called the modified Wentworth roundness index, which is really a measure of angularity. And this was used by the original conglomerates paper by Williams et al. 2013, which is why we sort of decided to start with this technique. So we can essentially compare apples to apples. She also has compared these values to Powers rounding, which is done visually by determining rounding using a scale that I'm sure a lot of us are familiar with here on the right. And just like with the grain size, she has used a grid by point technique to get at rounding, and we tried to get data for as many grains as possible for these rocks. And so one of the things that we've been able to see so far is that the clasts in these conglomerates have variable rounding from subangular to rounded. And so if we actually take the median rounding for each rock, we see that some have, like I said, subangular to ultimately rounded, which is what we have shown here in these images. It's just showing some of the diversity of the rocks that we have seen. And we also haven't seen so far any drastic stratigraphic trends, at least not yet. it takes a long time actually to do this rounding measurement. And so for these measurements, Tatiana has been using the Mali camera, so the highest resolution images. And so there are actually a ton of more grains that you can actually see, and so this is why it takes a long time. And so we want to fill in some of these gaps here. We have a ton of images and a ton of rocks, and hopefully over time we'll be able to see if we see any stratigraphic trends. And the reason that we're interested in this is because for these conglomerates, stratigraphic elevation also corresponds to potentially distance away from source, since we do think that the crater rim was the source. And so higher in stratigraphy is potentially further away from source. And so we might be able to see how, again, the rounding of these clasts changes with distance from source. And in addition, we also have grain size and compositional data for individual clasts. And so we might be able to not only quantify the rounding for the class, but also make estimates of the composition and see whether we see, rounding variation with composition or rounding variation with grain size for these individual rocks, and also from different stratigraphic layers. And so hopefully that will allow us to paint a larger picture for the transport history of these Martian conglomerates. And then just to end, I will say that not all the conglomerates imaged by Curiosity are in place. Some of them occur as float rocks in regions that we call heterolithic units. And so these are marked in yellow here on the left. And the general consensus is that these float rocks, so these are just individual cobbles and boulders of conglomerates, originated from Mount Sharp. So they originated from in-place units on Mount Sharp that were transported down essentially the mound by mass wasting. And again, they're out of place. And some of these rocks that we have analyzed so far have rounding values similar to those interpreted to be fluvial at the landing site, which raises the possibility that we actually may be encountering river deposits again on our trek up Mount Sharp, which again is sort of what Curiosity is sort of actively doing. And so we're actually getting snapshots of what's to come. And so with that, I'm just gonna put the take-home points there because I know I'm a little over time. And thank you so much again for tuning in, and hopefully I'll answer some questions. Thank you again.
Thank you, Dr. Rivera Hernandez, for an excellent talk. Please, everybody, start posting your questions to the chat, and then we can start taking questions from now. And if you can, you can also unmute yourself and ask the question by yourself too.
Hello, I have a question.
Yeah, go ahead.
Thanks for the cool talk. When looking at places like Mount Sharp and Jezero crater, we see clear signs that there's been lots of erosion in the past few billions of years. And so when we look at your deltas, and I think people have argued the same for the Achille Heineck paper from 2010, that we're not actually seeing a delta front because massive amounts of erosion has happened. And so wouldn't this be true for you showing a delta front on yours when that's probably just an erosional remnant from a much bigger delta from the past? Thanks.
Yeah, thank you for that question, Mike. So one of the things that I was very careful about, and I, of course, due to time, I didn't spend a lot of time on methods, is that I actually did see a lot of fan-shaped landforms in this region that I purposely did not include in my inventory because they very clearly had evidence of erosion. And so they had gullying. I actually did very detailed analyses across the delta front to make sure that the elevation across that arcuate shape of the delta front was generally consistent for each individual delta. And so I actually did have to filter out some features that clearly looked like they were eroded back, and they might be examples of what you suggested, potential deltas that were larger and then have been eroded back. But all of the landforms that I ultimately classified as deltaic deposits in my study, again, I did very detailed because we have actually higher resolution images now from the time that Gale and Hynek did their study. We have very high resolution context images that are at 5 meters per pixel. We also have high-rise images that is a different camera that's at 25 centimeters per pixel. And we also have DEMs made from both. And like I said, I spent several months doing very detailed work with each landform to make sure, again, that I didn't see any significant amount of erosion. And again, that front elevation was consistent throughout each individual landform.
Okay, thanks.
Yeah, that's a great question.
So I see Mark Johnson says they have a question.
Yeah, can you hear me?
Yeah, we
Can you hear me? Yeah, I just want to say I'm in Western Sweden, and I'm in a room with about 8 students and a couple of profs here, and we have really enjoyed this this talk. It's wonderful geomorphology, wonderful sedimentology. We on the west coast of Sweden, we have Gilbert deltas and shorelines at different levels, and it was fun just to see the same thing on Mars. But one question on Earth. Debris flows are an important part of alluvial fan genesis. Do you have any evidence that some of your fans have that the conglomerates are debris flow deposits rather than fluvial deposits?
Possibly. So I purposely focused on conglomerates that the rover image that we clearly had, saw well-rounded clasts for that analysis, but there are actually other conglomerates that have very angular clasts that might be evidence for debris flow deposits. And we also expect likely debris flow deposits further up Mount Sharp, since some of those float rocks that I was talking about, I did mention that some of them have well-rounded clasts, but some of them also have very angular clasts. And we think that they might be chunks from debris flow deposits further up Mount Sharp. So yes, I purposely didn't talk about it because I was focusing on river deposits, but yes, we do see evidence or potential evidence for debris flow deposits on sort of with the rover.
All right. Thank you for that. I think we have one question from Sinead. It was wondering, how did you estimate the flow velocities? What other paleo-hydraulic information did you have, like example, depth or slope?
Yes, so we actually had to make a ton of assumptions because, again, we're dealing with another planetary body, and the fact that we can even do these calculations, it's amazing. And so I have an extra slide I figured somebody was going to ask. And so we actually ended up having to make a ton of assumptions. We had to make assumptions about the critical shear stress. And so we had, a min and a max to sort of span the sort of typical values that we would see for gravel bedded rivers here on Earth. We also had to make assumptions about the slope values. And a lot of these conglomerates are thought to be associated with that Peace Vallis fan. And we do have slope values for that. And so that has provided a sort of a maximum slope that we've been using, this 0.01. And then we purposely just picked something a little bit steeper than that as well. And then I think the densities are pretty obvious. Of course, gravity changes a little bit because we are on Mars. And so that is something else that we have to take into consideration. And then we have this constant here that is a constant. And so we did have to make a lot of assumptions, but these are sort of the equations that we use. And I don't want to spend too much time talking about sediment transport just to make sure that I have time for the other equations. But if you want to learn more, I use the same techniques that are in Williams et al. 2013 and Dietrich et al. 2017. And I made the same assumptions as them. Thank you for that great question. Well, like I said, we do have to make a lot of assumptions because there's a lot that we don't know for these deposits on Mars. And over time, my collaborator on this work, Dr. Marissa Pelousas, is going to help provide some better constraints on some of these numbers.
All right, thanks. We now have a question from Mikael directly from Edinburgh.
Hi, yeah, I really enjoyed the talk, and I have a question about the pebble roundness. So you presented data with the median roundness, and I was wondering how much variability there was, like in the deposit, and in particular relating to Mark's question about, like, do you have some deposits that show pebbles that all have similar degree of rounding that would suggest one source and all the sediment is being transported together, and some deposit that will be more varied that will suggest more like debris flow deposits, like integrating sediment from multiple sources. I'm wondering whether you looked into the distribution of the roundness.
Yes, short answer is yes. We also are very aware that rounding can also vary with grain size. And so one of the other things that Tatiana has been doing, because she has been using that grid to point technique, she is also getting grain size with the rounding, which I did not show today.
Okay, right.
But we do have, you know, plots of grain size versus rounding, and again we have compositional
Okay.
data, and so we'll have a lot of axes or parameters to compare to each other. And so hopefully next year we'll have a more updated talk on
Sounds
all this.
good. I will look forward to publications. Thank you.
Yeah, thank you for that great question.
All right, so let's see. I think that I lost my Zoom screen. Yeah. So, and I think that in the interest. Oh, there's
There-
another question there. Yeah,
Yep,
go ahead.
yep. There's one question from Nigar Sultani. Thank you for a nice talk to calculate EU asterisk, but which way is useful for the Mars?
Yes. So if Marissa was here, I would defer to Marissa since she does most of the paleo flow calculations for my work. If you have a more detailed question, I probably would be able to answer. But I'm not sure.
I might risk and say that if you're already kind of assuming a shear stress and a density, you just get U star from those two. There's U star is tau over rho square root of that. I think it might go along that way. But yeah, if Marisa did this, that might be best to get in touch with her. All right, I guess in the interest of time, I just want to thank you, Francis, again for sharing aspects of your research. As Mikael said, we look forward to future research outputs from your group to continue to learn from planetary surface processes and environments. Thank you to all those who joined today. And then Bishwadeep is going to share details for our next month seminar.
Yep.
Great,
So
good.
a quick reminder for everyone that our next EPSP Connect seminar will take place on October 15th at the same time. Our speaker will be Dr. Rachel Glade from the University of Rochester, who will give a talk entitled Low-Bed Soil Patterns on Earth and Mars, Finding the Secret Recipe.
All right, we will continue to explore Mars. Thanks, everyone.
Yes. Yep. Thank you, everyone.
Thank you, everybody. Have a good day.
Thanks, everyone.